Hi there, everyone. My name is Mario. I'll be presenting the second session and the second keynote. This keynote will be on fair or robust, addressing competing constraints in federated learning. The presenter is Virginia Smith. She's an assistant professor in machine learning department at Carnegie Mellon University. Her research spans machine learning, optimization, and distributed systems. Virginia's work addresses challenges related to optimization, privacy, fairness, and robustness in distributed settings in order to make federated and non-device learning safe, efficient, and reliable. Her work has been recognized by numerous awards, including MIT Innovator Award, Facebook Faculty Award, Google Research Award, and so on. Prior to CMU, Virginia was a postdoc at Stanford University and received her PhD in computer science from UC Berkeley. So without further ado, Virginia, if you want to take over and present.
Awesome. Thanks. Thank you for the introduction. Excited to be here today. Let me go ahead and try sharing my screen. I apologize. It's a little bit earlier here on the East Coast in the US. So sorry if I'm a little bit slow today getting set up. Can you see my slides?
Yes, we can. Virginia, is it okay to record your talk?
Yes, yep.
Great, thanks.
Cool, and please do feel free to stop me at any point if you have questions. I'll try to monitor the chat window or look for, the raised hand feature, or just feel free to unmute yourself and ask a question if you want to jump in. So today I'm going to be talking about fairness and robustness in federated networks. I'm going to talk about in what ways these are competing constraints and in what ways they compete with other constraints that we also care about, like privacy and accuracy. And I'm going to see if there's any way to address these constraints simultaneously, or if they're fundamentally at odds with one another. And one of the key ideas I'll be talking about here is some techniques for personalized federated learning. So before I do that, let me just start with a working definition of federated learning. I'm assuming that many of the folks in the audience are familiar with federated learning, but the workflow that I'm going to be imagining and the goal of federated learning is basically just to train machine learning models at the edge. So there can be a lot of benefits to doing this. This can allow you to more quickly incorporate new data that you're seeing at the edge. There can be computational or communication benefits to pushing things to the edge, so this can reduce strain on the network. And there can also be some privacy benefits for keeping the raw data local on each of the devices. Okay, so here's the sort of typical workflow that we'll be thinking about specifically for sort of cross-device federated learning. So the objective is typically some empirical risk minimization objective. You're minimizing a sum of losses across your n different devices in the network. And to do so, you communicate back and forth between a central server or a node and the devices. And typically in the cross-device setting, there might be millions, thousands to millions of devices. And at each round, we communicate with only a subset of them. Okay, so this workflow at a high level is reminiscent of traditional work in distributed computing and distributed learning. In particular, the diagram that I have here looks a lot like traditional data center computing. But there are a few challenges that have emerged that really make this setting distinct. So one is just the scale and the characteristics of the network. So unlike something like the data center, where you may be working with hundreds to thousands of machines, here you might be working with thousands to millions, maybe billions of devices. So there's the networks can be very, very massive. They can also be slow, and they can be quite unreliable. So if you're using these user devices as a computing substrate, you might have issues where someone turns off their phone or they lose connection. And for that reason, it's a very unreliable set of nodes that you're possibly learning over. Okay, we also motivated federated learning by talking about the issue of privacy. So privacy can be a big concern in this setting. You are improving this potentially by keeping some of the raw data local on each of the devices, but we're still communicating something over the network. So it's critical to think about how to ensure that those messages are secure and that we're not leaking any private information. Okay, and then finally, a major way that this setting differs from something like the data center is because all of the devices are generating data and that raw data is remaining local to those devices, there can be a lot of heterogeneity in the network. So this can either be due just to unbalanced data, so some devices might be generating more data than others, or it could be because the data is non-identically distributed. So some devices generate data that looks different than the data on other devices. And this heterogeneity and diversity can exist not only in terms of the data, but also possibly in terms of the underlying systems characteristics as well. So each of these devices might have variability in terms of the hardware or connectivity or power, and all of this can really affect how capable each of these devices are at participating in the training procedure. Let me stop here because I think there was a question. Okay, that was from the previous talk, I think. So I'm going to talk about all of these concerns today. I'm going to touch on all of them, but my focus is specifically going to be on this issue of heterogeneity. Again, this is one thing that really differentiates this setting from traditional data center computing. So in thinking about heterogeneity, there's a few questions that I'm going to visit. So one is, how does heterogeneity, this issue of the data being diverse or the devices having diverse computing capabilities, how does this affect our training procedure? How does it affect the federated optimization methods that we run in this setting and the corresponding sort of convergence guarantees that we can provide for them? Okay, but it turns out that the effect of heterogeneity doesn't just, manifest in terms of the optimization methods, right? In terms of our training procedure. It also affects the end performance of the model that we train. And a major question here, if you have very diverse data or very heterogeneous data, is how you can provide a reasonable quality of service for your entire network. And one way to view this issue of fairness or quality of service is thinking about how you can roughly equalize performance across possibly very diverse networks. And this actually brings up sort of a more fundamental question, which is how should we really be modeling data coming from these user devices where the local distributions might be differing from one device to another. And the key thing that I'll be looking at here is how we can personalize models in federated settings and how can we can do this at scale across very massive, possibly unreliable networks. And what we'll see is that actually thinking about this sort of top of the stack issue, how can we provide personalized models, has implications for all of these other components as well. So it has implications for fairness, which I'll talk a bit about, but also for the issue of robustness. It has some implications for privacy and for how we actually solve these methods, so for the optimization method itself. Okay, so this is a rough breakdown of the high-level topics I'll be talking about today. I'm going to talk about very briefly some key ideas in federated optimization. Federated optimization itself has become a really massive field, so I'm just going to mention some high-level takeaways from sort of general techniques to consider in thinking about optimization in federated networks. And then I'm going to spend the remainder of the talk talking about, in some ways, what is sort of a more fundamental issue, which is before you even solve the objective, what is the objective that you should be solving? How should we be modeling data in federated networks? So I'm going to talk about the issue of fairness, and then I'm going to talk about personalization, and we'll see how this ties back to this main question that I started the talk title with, which is thinking about fairness and robustness and these competing constraints. Okay. Are there any questions here before I jump in? Yeah, please. Can you please point to the model? Is it the same for all devices? So the standard objective that I'll be using as a baseline is just training a single global model. So I presented that very briefly on this slide. So the way that objective might look, it might be just a traditional sort of empirical risk minimization objective where you have n different devices and each device has its own local data. And for that local data, you're solving some aggregate set of losses across the local data. So F sub K of W would be how, measuring how well the model W fits to the local data on device K. And the goal is just to minimize this set of losses across all of your n devices while training a single model W. So this is what I'm going to view as the baseline. All right, so let me touch on optimization really quickly because it's a critical part of this. How do we actually solve these federated learning objectives? I just want to point out that there are a number of key challenges here to consider when doing this in the federated network. So one of the challenges is how we can do this while reducing communication costs. And there's been a lot of work thinking about how to do this, both in traditional data center computing and in federated learning. And it turns out that one of the most popular approaches in federated learning to really reduce communication costs is something that was also developed in the data center setting, but it's turned out to be very effective for federated networks of possibly millions of devices, which is this sort of simple idea of using local updating, which is that rather than just running something like traditional gradient descent or mini batch version of gradient descent, what you do is on each of the devices, you actually run some iterations of a local solver. And it turns out that by doing more of this computation, more work locally, you can often significantly reduce the number of communication rounds required to converge to a good solution. Okay, sort of directly competing with this though, with the sort of communication benefits that you get from these local updating methods, is then understanding how these local updating optimization methods perform in heterogeneous networks. So there's been a ton of work trying to understand both the practical and theoretical convergence guarantee, performance and guarantees of these local updating optimization methods. So there's been a tremendous amount of work thinking about how to support this approach when you have possibly very heterogeneous data across the network. Okay, another key challenge here is thinking about how to effectively combine privacy and optimization. This is something that goes well beyond just the federated setting, but it's particularly important for federated learning because privacy is a major motivation for why we want to do this in the first place. Okay, and lastly, I wanted to mention, so I'm actually currently working at Google 1 day a week. I'm working part-time with the federated learning team there. And one thing that I've discovered in actually thinking about these systems in practice is that another key challenge here in terms of optimization for federated learning is that very simple things that we can do in traditional settings like hyperparameter tuning become very, very difficult now when you're doing them over a set of millions of unreliable devices. So we have some work also in this area in terms of thinking about hyperparameter tuning at scale in federated networks. Okay, again, I'm not going to spend most of the talk on optimization, but I just wanted to provide a few resources. Again, this is a very active area of research. There's a lot of work going on in this direction. Related to that, I wanted to point out one resource in particular, which is a recent work with a large group of people looking at developing a field guide to federated optimization. So this provides both a high-level overview of the kind of general trends that we're seeing in terms of federated optimization and some best practices for thinking about how to evaluate these methods and analyze them. Is this the same Adam Smith? Oh no, this is Smith. This is Virginia Smith. So I'm pointing out some of my own work here in terms of these the papers that I'm citing. Okay. And this is obviously a very small subset of work that's being done in this area, but I'm just pointing out some of my own work in terms of thinking about federated optimization. Okay. One other thing I wanted to point out really quickly, if you're interested in federated learning generally, I run a flow seminar. So this is a federated learning one world seminar. It's a weekly seminar that is global across the world. We have a lot of participants from many, many different countries. And it's been exciting to run this just to keep on top of current research in federated learning and have the ability to have sort of an open discussion with folks working in this community. So if you're interested in this area, I'd highly recommend to check out some of these seminars, which run weekly every Wednesday. Okay, so let me get to the remainder of the talk here. I wanted to just mention optimization because it's such a critical part of this pipeline, and there's a ton of work in federated optimization. But what I want to spend the remainder of the talk on is something which, again, I think is even more fundamental in some sense, which is forgetting about how we solve the objective. What is the actual objective that we're solving in federated settings? And what objective should we be solving? And I'm going to talk about a few different issues here. So I'm going to first talk about the issue of fairness in federated learning. And then I'm going to talk a bit more about some of the other constraints that we might care about. So accuracy on each of the devices and robustness and privacy. Okay. So first, let me talk a little bit about this issue of fairness. Fairness, there's a lot of work in fair machine learning. Fairness takes many different sorts of definitions. So what exactly do I mean when I say fair federated learning? To think about this, let me start with sort of what the baseline is typically in federated learning. So I mentioned this initially, often the objective that we're solving is some sort of empirical risk minimization objective. We're trying to minimize typically just an average of the losses across the n different devices in the network. Okay, and this is a very common approach, and it works very well if what you care about is average performance. But an obvious downside is that there's no real accuracy guarantee for the individual devices, right? You're minimizing the average performance, but there's no guarantee about what the actual performance will be on any one of the individual devices. And so what you might see is that you might do well on average while having the performance, the accuracy of the model on each of the devices vary quite widely across the network. Okay, and so this is what you might see. This is an example just on a very common federated learning benchmark. If you look at the histogram, so if you look at the distribution of the test accuracy after training a model via traditional empirical risk minimization, you might see a performance that looks like this. Basically, what you see is that on many of the devices, you're doing pretty well. But on a few of the devices, some subpopulations in the network, you have pretty terrible performance. And this is something that you really might want to prevent in practice. So forgetting about the issue of fairness for a second, if you're deploying an application across a bunch of devices, you might want to ensure that you don't have these issues where you have sort of catastrophic failures of the model, right? So we want to provide some reasonable quality of service of the model. We want to have some assurance that the model won't be doing very bizarre or having the sort of terrible performance on a subset of the devices. Okay, and so this is the question that we asked ourselves in this work. Basically, can we encourage a more fair or uniform distribution of the model performance across devices, particularly in light of the fact that data is often quite heterogeneous in federated networks? Okay, and to solve this problem, we were actually inspired by a very sort of related problem, but in a different area, which is the problem of fair resource allocation in sensor networks. So broadly, the goal of fair resource allocation in a sensor network might be to fairly allocate a resource like bandwidth across the different devices. Okay, but to draw an analogy to machine learning and to this empirical risk minimization objective, the way you could think about the resource that we're sharing by solving this objective is these losses, right? So basically, if a loss is large on a particular device, then our model is going to spend more effort fitting to that particular device and that particular device's data. Okay, so using this analogy, we formulated the following objectives. So this is again inspired by this notion of alpha fairness, which is used for fair resource allocation in wireless networks. And using kind of this inspiration, we developed the following modified version of empirical risk minimization. Basically, all we're doing is we're taking the losses and we're raising them to some exponent q. Okay, and the way to think about this basically is that if you had a loss that was fairly large, right, depending on this value of q, the effect of raising it to this exponent, q plus 1 here, is that large loss is going to be magnified. It's going to become even larger. Okay, and there's a couple extremes to sort of consider here in terms of understanding what this objective is doing. So first, if q is 0, you just get back the traditional empirical risk minimization objective, right? If q becomes larger and larger, as q goes towards infinity, you get back a very common notion of fairness that's been explored both in the machine learning literature and in the federated learning literature. So it's this min-max notion of fairness. It's often referred to as representation disparity. The goal is basically that you want to minimize the worst performing loss on any one of the devices in the network. Okay, but it turns out that thinking about this not in either of those two extremes, so having this tunable framework between ERM, traditional averaging of the losses, or this min-max notion of fairness, can be quite useful in practice. So what we found is that for one, this objective is easier to solve when you're not just thinking about the q equal infinity approach. But two, there can be real reasons why in practice it's useful to sort of trade off between this notion of fairness or the notion of average accuracy, right? So just to give you one example of this, if we look back at the previous objective that we were looking at, this previous common federated learning benchmark, and we look at the test accuracy distribution after using this objective, which we're calling Q fair federated learning, you can see performance that looks like this. And the way that we've solved this objective is that we're actually getting the exact same average accuracy. You can see though that the variance here is basically becoming smaller, right? And in particular, what you can see is that we're able to improve these worst performing devices. Okay, and we can improve them by a significant margin, right? So this is something where we're really going from sort of this catastrophic failure of the model to something that's much more reasonable. How are we doing this? Obviously, it's not coming for free, right? The way that we're reducing the variance, basically we're doing just as well on average. We're performing slightly worse on the best performing devices, But by doing so, we can enable a better quality of service for the devices in the network. Okay, and I'm not going to go into too many details of this plot because there's a lot going on here. But just a high-level punchline: we've looked at this approach across a bunch of different federated learning data sets, and what we can see is that on average, we can cut the variance of the accuracy distribution in half, while maintaining the exact same average accuracy. Right. So at first blush, you're not really losing anything, right? In the sense that you're, often the metric we report is the average accuracy across the devices, right? We're getting the exact same average accuracy. We're just helping to reduce the variance so you don't have this extremely wide variability of the performance of the model in the network. Okay, and I wanted to bring up one more thing here, which is that this has also inspired some work going beyond just the federated setting. So we have looked at an extension of this objective as well, which we're calling tilted empirical risk minimization. It's actually quite similar to the objective on the previous slide. We're just using basically an exponentiated version so that the exponent q now becomes just multiplied by the loss function. But crucially, we're also exploring allowing this parameter q, or here t, to be either positive or negative. And the implications of that are that you can think about what this parameter is doing as basically sort of reweighting the samples to either magnify or suppress the effective outliers. If we're thinking about the issue of fairness, right, what we're doing effectively is we're taking the diverse points, the outliers, and we're magnifying those points. Alternatively, it could be that you want those outliers to be suppressed, right? They could be noisy data, they could be some adversarial data. And so you could think about making this parameter positive or negative to reflect what you know about those outliers. So it turns out this is actually, in some ways, a very, very simple baseline, but it happens to be very, very competitive for a lot of current applications in deep learning and thinking about things like dealing with class imbalance, or dealing with corrupted data, or dealing with issues of fairness, or just improving generalization and to be robust to some sort of distribution shift. So this is actually a very, very general approach. It goes beyond just the federated setting, and it's something that we've looked at in some recent work, understanding sort of general properties of this objective and how effective it might be as a baseline for a bunch of different applications in machine learning. Okay. All right, so that was sort of an aside there, but I just wanted to mention that because a lot of this work, even though we're focused really typically on this application of federated learning, extends to other sort of core ideas in machine learning as well. All right, let me summarize here quickly some of the main ideas from this section on fairness, and then I want to talk about not only the issue of fairness, but other issues that you might see in federated networks as well, like the issue of robustness. Okay, so high level, sort of the punchlines from this section, I think the main idea is just that vanilla empirical risk minimization, just solving for the average accuracy, might deliver poor quality of service when you have very heterogeneous or diverse networks. And the objectives that I talked about, Q, fair federated learning, and term, allow for flexible trade-offs between fairness and accuracy. So these can be very effective when you want to be able to tune the amount of emphasis on something like fairness or equalized performance across the devices versus accuracy metric like the average accuracy across the network. Really quick, I think there's a question. Okay, so for the first presented formulation, when Q is greater than 1, we can lose convexity because x to the q is convex, but not increasing in all function domain. So actually, if these losses are convex, then this should still be convex. The issue happens if q is less than 0. So in the term work, if this parameter t in particular is less than 0, then this can become non-convex. Although I think the sort of meta point that you brought up is often in federated learning, we're thinking about non-convex objectives to start with. But actually, if these functions f are convex, then this objective will still be convex. All right, so let's talk a little bit about something really at the top of the stack. So we talked about this objective for if you want to train just a single model, how can you force it to sort of trade off between fairness and accuracy? But maybe an even bigger question is, should we be training just one model, right, in federated networks? If they're truly very heterogeneous, how should we actually be modeling this data? And this is, again, it's a very fundamental question. It's sort of the first thing that we asked ourselves when we started working in federated learning several years ago. And there's two natural baselines, right? So the first baseline is just that if you have a network of devices, I'm drawing them to different scales just to represent the fact that they could each have, different amounts of data, or the data might look different across the different devices. But the first baseline is that you could just train a local model for each of the devices, right? This is sort of the easiest thing you could do because it requires no communication across the network. But the downside to this, and the whole reason that we've been focusing on federated learning, is that there's some belief, hopefully, that sharing this data can be useful, right? And in particular, what you see is that if you're thinking about learning over something like mobile phones or IoT devices, often these devices don't collect enough rich data to power their own local models, right? Think about something like, thinking about a language model, or, speech detection or next word prediction. Often there's, you just don't, see enough words or enough text or enough speech on a single person's phone to really generate a rich model for that particular user, right? And so this brings us to sort of the federated learning approach, the standard baseline, which is to just train one model across all of the devices. And this is nice from the perspective that allows us to really boost the effective sample size of each of the data sets on each of these devices. It allows us to learn from peers in the network. But one potential downside is that if this data is truly heterogeneous, it's very different possibly from one device to another, learning just a single model doesn't inherently allow you to provide personalized behavior, right? To learn personalized models, one for each device in the network. Okay, and so what we were looking for when we first started thinking about this problem is something in between these two extremes, right? We wanted to be able to learn these personalized models, one for each device in the network, but we also wanted to be able to learn from relevant or related devices, right? We wanted to learn in a smart way. We wanted to figure out which devices are related to one another, and then we wanted to learn between the devices that are most related. And this is something, it turns out, that's very naturally captured through a common framework known as multitask learning. Okay, and this is very old work, I guess, at this point, but I'm going to talk about this high-level objective, and then some more recent approaches that really make this scalable and practical in federated networks. Okay, but the high-level idea in multitask learning is the following. Basically, you learn a separate model, W sub t, for each device. So here there are m different devices in the network. And we have, a loss just like before. Basically, you're trying to make sure that local model, WT, is a good fit to the data that's generated on device T. Okay, but in addition to these local models that we're learning, we also are doing something interesting here. So we are also including this regularization term in the objective. And what this regularizer does is, for all of the models, which are now encapsulated in this matrix W, we try to learn some structure between those models via this matrix omega, which is known as the task relationship matrix. Okay, so at a high level, what's going on here is what we're doing is that we're learning these personalized models, but we're also learning and enforcing some structure between those models. So this structure can take many forms. We might learn that all of the tasks or all of the devices are related to one another. And what we're learning as part of this objective is that we're learning the weights on the edges in this graph. Okay, or we might learn that there are outliers that exist. Some devices are maybe, quite unrelated to the other devices. Or this is a really natural one that we've looked at for a bunch of applications in federated learning. We might learn that clusters or groups form in the network. So there are clusters of devices that are related to one another, or potentially that there's some asymmetric relationship. Maybe there's sort of one power device that's generating most of the interesting information in the network. Okay, so this is an objective that we've looked at for, at this point, a bunch of applications in federated learning. And it can be very effective at basically going in between these local and global baselines. So depending on how much heterogeneity you have in the network, if you have tons of heterogeneity, you sort of want to go towards a completely local baseline. If you have no heterogeneity, if everything is homogeneous, then it's simple to just train a global model. And what multitask learning does is it allows you to go between these extremes and also learn this sort of very useful information, which is information about how the devices are related to one another. Okay, but There's one downside to this approach, which is, this is again sort of old work at this point. This was an objective that we proposed in 2017 for thinking about how to, solve the problem of learning in federated networks. And one issue is that if you have to learn this entire task relationship matrix omega, this is an M by M matrix where M is the number of devices in the network. So this is something that really is not feasible if you have to learn over millions of devices, learning the entire relationship between all of the devices in the network. Okay, and so to deal with this, there's been a number of other scalable approaches proposed for federated multitask learning. And I'm going to talk about one today, which is in some sense going back to sort of the very basics. It's a very, very simple approach for multitask learning. So I realize there's a lot on the slide here, but it's actually pretty simple what it's doing. Basically, what you're doing is you're learning separate models, again, one for each device in the network. And the only way that we're enforcing these models to be related to one another is that we're forcing them to be in some ways close to the global model W star. Okay, so you can think about this multitask objective as sort of trading off between two things. One is training a global model across all of the devices, and the other is that local baseline. And the idea here is that we're basically forcing the local model, the local baseline, the one that's trained just on the local data on each of the devices, to be relatively close via this proximal term to the global model W star. Okay, so you can think about this as maybe being one of the simplest forms of multitask learning, right? The way that we're ensuring personalization and sharing between the personalized models is we're just ensuring that they're close to the global model via this L2 distance. Okay, it's worth noting this is also very scalable because it's very simple to solve this objective, right? We've already talked about federated optimization for training a global model. Basically, the only difference here is that you trade off between fitting a global model to the data and doing some local fine tuning, right? So you can trade off between solving this model W star and the local models WK. Okay, and one reason this is really nice, in particular, this sort of simple form of multitask learning, is that it preserves kind of common mechanisms for enforcing privacy in federated settings and for using communication efficient solvers for solving the global model. Right, so we're really not adding on much additional computation, and we're adding on no communication on top of just the global baselines. Okay, just to show you what this looks like, basically all we're doing in terms of the method itself is that we're training a global model just like you normally would. You can imagine this being a common federated optimization method like federated averaging. And then on top of that, we're performing some local personalization. So at every communication round, we're basically just doing some updates to the local model, which I'm calling V sub K here. Okay, this is very modular. So I talked about this at a high level, but in terms of solving this, you can plug in any global solver that you want. You could use federated averaging, some other methods, scaffold, fedprox, whatever method it is that you want to use, and you inherit the convergence behavior of that global solver. Okay, it also has these privacy benefits. So it preserves the sort of, we're doing the exact same communication that we were previously in terms of solving the global objective. So it preserves the communication and privacy benefits of solving that objective. And what we'll see though, which I think maybe in some ways is surprising, is that this very, very simple form of multitask learning can have tremendous benefits, not just in terms of the accuracy, so providing these personalized models for better accuracy, but also in terms of things like fairness and robustness. Okay, so let me talk about that in a bit more detail. So this is a very small sample of the results. We've looked at the performance of this method, which we're calling ditto, this very simple form of multitask learning across a bunch of different federated applications. And what you can see is that it's able to, again, sort of go between these local and global baselines. So you can improve just the average accuracy across the network. Okay, but you also see this interesting behavior where, and I think this is actually something that's pretty intuitive, but it's worth pointing out, which is that if you're not training just one global model, if you allow for personalization, then there's less of an emphasis on this global model and less of an ability for an attacker to sort of ruin that model for everyone, right? So it has some robustness benefits as well. If you have data that's become corrupted in the network, or you have a malicious device in the network, that device can start to sort of mar the utility of the global model that's being trained. And by learning these personalized models, it can help to sort of reduce the reliance on just that global model. And the results here, what we found, it's pretty extreme. So if you look at multitask learning, which is shown here in blue, this is just a simple ditto objective. We're looking at the testing accuracy as we increase the number of malicious devices in the network. And what you can see is that the accuracy remains quite high for this multitask learning objective, even compared to common robustness baselines like multi-crum. So we've looked at a bunch of other robust baselines as well. This is one of the best performing ones. And you can see that when just training a global model with some sort of robust baseline that gets rid of the sort of tail behavior, you can see that this starts to deteriorate significantly more than just this sort of simple baseline of training a multitask model. Okay, and on the other hand, we also see benefits in terms of fairness, right? So we talked in the earlier part of this talk about this, these approaches, QFFL and term, for providing a fair global model. It turns out that maybe there's even a simpler baseline, which is, just solving this multitask objective has inherent fairness benefits. So if you look, for example, at the accuracy variance, this is one of the measures that we had been talking about as a notion of fairness. How much variation is there in terms of the accuracy distribution? And you look at this for the multitask model compared to training the sort of state-of-the-art fair baseline that we talked about previously in the talk, you can see that just by using multitask learning, you're getting fairness benefits. I think this is also quite intuitive, right? Because you're training these personalized models, you don't have this tension where one global model needs to perform well across all of this very diverse data, right? And so you can enable personalized behavior that helps to reduce this accuracy variance across the network. Okay, there's something else sort of hidden here, which is the main thesis of this talk. It's the main title of this talk, and you may be seeing it already, right? But the high level idea as well is that I talked about these two issues, robustness and fairness, and how multitask learning has sort of inherent benefits in terms of both of these approaches. But what you can also see is that there's a real tension between fairness and robustness, right? So if we look at the robustness plot here, and we look at the fair baseline, what is the fair baseline doing? It's taking the outlier points, it's taking the devices that look very different, and it's magnifying those devices, right? It's increasing the importance of those devices. And what happens is when you have a lot of malicious devices, right? You have devices where some data is corrupted or there's some adversary in the network, those devices might look diverse, right? They might look like heterogeneous devices. And by using a fair baseline, what we can see is we can start to overfit to those malicious devices. So the fair baseline in particular becomes really, really bad in this setting where there are attacks in the network. Okay, and then on the flip side, what you see is that if you just use a robust baseline, it can result in unfairness, right? You might have very large accuracy variance. And again, this is, I think, intuitive. What is the robust baseline doing? Typically, a method is robust because it's getting rid of that tail behavior. It's getting rid of the behavior that might possibly be malicious. And if that's not malicious, if the data is just heterogeneous, then you're getting rid of important and diverse data in the network. Okay, and so sort of the key punchline of this work is that not only does multitask learning and personalization in the federated setting provide robustness benefits and fairness benefits, but it's also really key for addressing these constraints simultaneously, exactly because sort of the common fair baselines overfit to the malicious devices, that the performance really starts to tank. And on the flip side, robust baselines get rid of that tail behavior. And so inherently, they're not providing fairness. Let me stop because I think there was a couple of questions. Okay, so there was a question actually going back to the task relationship objective and omega. So this is actually an important part of this objective. So I'm just going to go back a couple slides. Sorry for not catching that earlier. So there was a question about how is omega defined. So omega is something that you're actually learning. So you're learning omega as part of this objective. Typically, you alternate between learning the models and learning the task relationship matrix omega. But a key part of instantiating this objective is deciding what this regularizer should look like. And I'll give you one example. So a very common regularizer that's used is this sort of clustered form of multitask learning. So the way that you can enforce clustering is basically you end up having a sort of trace constraint on this matrix omega. That's a convex relaxation of what you might really want, which is that you want to enforce that omega is low rank. But by having that trace constraint, you can ensure that, that you're learning basically clusters or groups in this matrix, that there's sort of, clustered pockets of information in the matrix omega. So there's a bunch of different instantiations of what this regularizer could look like, just to answer that question directly. But this is the key thing here is that you're actually learning omega. So if you know information about omega, you can put that in beforehand, but more commonly you learn it directly as part of this optimizing this objective. Okay. Oh, I think the last question is quite interesting about continual federated learning. I think I'm going to probably touch on that in the last couple of slides, so I might come back to that in just a minute. Let me see, I want to make sure I end on time, so I might, let's see what I have left. I might skip this part. So this is just some additional details in terms of how we're setting up our definitions of robustness, some of the attacks that we look at, and our definition of fairness. And again, I'm just going to repeat myself here, but sort of the key punchlines are that even for this extremely simple form of multitask learning, what we can see is that it has inherent fairness benefits, so that it's performing even better than state-of-the-art, fair federated learning approaches. Just by learning these personalized models, you have some benefits of fairness. Okay. Similarly, if we're looking at we looked at a ton of different robust baselines. This is a very small sample here. But what we found across a bunch of different attacks is that on average, if we look at the next best sort of robust baseline, we can improve accuracy on average by 6%. So that's an absolute number. So we're significantly improving the accuracy. And we're doing this just by using this multitask objective, just by enabling personalization. Okay, and then the key punchline is, and this is, I guess, a lot to see in a plot, but the high level idea here is that in practice, you really care about two things, right? You often care not just about fairness or robustness in isolation, you probably care about all of these together, right? And so if you care about reducing the variance on the y-axis and improving the test accuracy on the x-axis here, what you can see is that there's a real tension between what you're able to do with just a fair or just a robust baseline. And ditto, this simple form of multitask learning, can help you to achieve both of these simultaneously. So it can improve the test accuracy while reducing the variance, so providing some notion of fairness, and it can do so even when you have corrupted devices in the network. Okay, so a few key takeaways here. I think the main thing I want to get across is just that personalization is important in federated learning, right? For sort of all of the benchmarks that we've looked at, personalization provides some improvement in terms of the accuracy, sometimes a very significant improvement, but it's also critical not just for sort of this average notion of accuracy, but also for practical constraints like robustness and fairness as well. And in particular, multitask learning is a really nice principled way to learn these personalized shared models in federated networks. Okay, in terms of what's next, I wanted to mention that there's one sort of last key constraint that I didn't talk about, which is privacy. We also have some recent work looking at formalizing notions of differential privacy for multitask objectives. And what we found here is sort of similar to the story that we've seen so far, which is that by using this multitask objective and by enabling differential privacy in this setting, so it's actually not extremely straightforward how to do that, but we've developed some methods for enabling differentially private multitask learning. You can improve the utility of these models while retaining the same privacy, right? So for the same sort of, across the sort of Pareto frontier of privacy and utility, privacy and accuracy, you can significantly improve things by using this differentially private multitask learning objective. Okay, one last thing I wanted to know, and then I want to get to that last question in the chat window. Even though we've I think come a long way in the last several years in terms of seeing more and more applications of what federated learning looks like in practice. Again, I mentioned I'm working at Google, and so I'm seeing some more of this firsthand now. I still think that to really move the field forward, we need more examples of what federated learning looks like for real applications. So along these lines, I developed the LEAF benchmark, which includes a suite of open source data sets, an evaluation framework, and this online presence to help encourage participation. But I think this is really critical and something that I'd like to continue iterating on. So if this is something that anyone is interested in collaborating on, please let me know. I think it's really critical, especially for something like heterogeneity, to know what this looks like in real federated networks, so that we can best solve and deal with these competing constraints of accuracy and robustness and fairness and privacy. Okay. Lastly, I wanted to mention, I didn't get to talk about this too much. I just kind of mentioned some of the benchmarks at a high level, but we've actually been looking, at a bunch of applications in my lab as well, beyond just sort of the standard mobile applications of federated learning. So we've been looking at federated learning for smart home modeling. We've been looking at it across networks of submersible vehicles, learning across microgrids and power grids, and in cross-silo applications like medical imaging detection as well. Okay. So thanks, that's all I had. I don't know if I have time. Maybe I'll try to answer this question really quick. I think the question was about if I have any insights about adapting multitask learning for continual federated learning, where the tasks of users are not just coming from non-IIDness, but they may be changing over time. So one thing I will say is that if you're solving the sort of multitask relationship learning objective that I talked about, there has been some work thinking about how to do this in a continual sense. And one thing that's nice about how the objective is solved is that you iterate between solving for the models and this task relationship matrix omega, so that if the models are changing, if they're changing, because of some new event that's happening or because a new device enters the network, for example, you can, develop that new model, and then you can, learn omega again, because you iterate doing this, back and forth. And so that's something that you could incorporate just sort of by the alternating nature of solving that objective. But in general, I will say one thing, this is actually kind of brings me back to the LEAF benchmark. One thing that I think would be very useful to spend more time on in federated learning is that there's a real lack of benchmarks dedicated to sort of this temporal, these temporal applications of federated learning, where data is coming in and streaming over time, and you care about doing some sort of time series, learning application. I think this is a super natural application of federated learning, but I don't see many benchmarks around it, unfortunately. And so that's something that I think would be very useful to try to incorporate.
Great. Thanks for your thought, Virginia. We need to resume. Very good presentation. I don't see any more questions for now, so I guess we can move forward to Konstantin has a question. If you can reply like super fast, like we might have like 2 more minutes, and then we can go on
sure.
later. Yeah, right.
So I think even though a lot of the question is about whether convex learning is important for places like Google, so I can't speak for for Google entirely, but I will say that certainly there are applications where convex optimization is also important. I think you pointed to one. Yeah, logistic regression is one. So basically, you can think about any sort of application that you have on the web can now be run on your phone. And so now you might want to be supporting that. So like one application that comes to mind where logistic regression would be incredibly useful is something like click-through rate prediction. Right? Logistic regression is a very common baseline that's used in click-through rate prediction. You might be trying to solve this click-through rate prediction, but now across a bunch of phones. So that's a really simple example where that convex objective would be very, very useful.
Great. Thank you very much, Virginia.